Welcome to the channel. This is our third video for Precalculus review for a Calculus 1 course. You can check out all the other videos in the playlist. I highly recommend making sure you understand all of this information. Today we're going to talk about transforming functions. So shifts and stretches, when we add and subtract numbers, we might multiply by a number as well. Translations, maybe also what you've heard of it as composite functions, or kind of functions that live inside another function, and we want to decompose those and look at that. Odd versus even, you'll sometimes hear this word parity as those, P-A-R-I-T-Y. And then finally, inverse functions. So let's get into it. So the first part of this video, we want to look at shifts and stretches. So this is fairly simple, but remember that a shift means it's moving it left, right, up, down, a translation, right? So left, right, or up, down, depending on where you're adding or subtracting some constant value. A stretch is going to be a multiple. You're multiplying by a constant. Multiple constant. So if I want to shift left or right, we are going to replace x with x minus k. And this will shift it k units. But remember, if you want to shift it to the left, it is going to be plus k. That's the nature of it. And the same thing for up, down. If I want it to go up, wherever I see a y or an f of x, I'm going to simply say y minus k. And I'll show you what I mean in a minute here. If I want to stretch it, let's use a different constant. So stretch or shrink really is how we want to think about it. Shrink. Well, if I multiply the whole function by a value of c, or if I have a value of c multiplying the x value, to be clear, you can have c times f of x or f of c times x to change the function. That's what I mean. Now, if c is greater than 1, it's going to be a stretch vertically. So this is a vertical stretch. Remember, this is a review, so we're not going too in-depth here. This would be a few videos maybe for a pre-calculus course. But if we're going to do this, this is a shrink, a vertical shrink. And if c is less than 1 or less than 0, if c is negative, it's going to also flip it or reflect. Okay? So we want to remember that. Typically across the x-axis, in addition to any shrinking or stretching based on the factor. So let's do a quick example here with x cubed. This is the parent function here for x cubed. It goes through the point 0, 0, and it goes to infinity as x gets really big, and goes to negative infinity as x gets really small. In the negative direction there, negative infinity, and as x gets big, it goes to infinity. Let's say I want to shift it up by 2 units. Well, the graph is going to go through this point, 0, 2, and the equation is going to be x cubed plus 2. Notice we're going to go back and say replace y or f of x with y minus k. So if the original function is f of x equals x cubed, then I'm saying I replace f of x minus 2 equals x cubed when you solve for a new function f of x, or let's call it g of x because it's a different function and with a shift. Well, it's shifted up by 2. Hopefully that is fairly obvious. Similarly, if I want to shift it to the right by 3, I know that it's going to go through the point 3, 0. We're shifting along the x-axis. And it's going to be some h of x, but really remember we're replacing with 3, so h of x minus 3 equals x minus 3 cubed, if the original function is just x cubed. And you should have a lot of practice with this, very familiar. Again, this is a review. So let's talk about a few more and then we'll move on to the next section. This will be a reflection, so if it still goes through 0, 0, and it's reflected now, notice that it goes to, as x gets really small, it gets really, really big, opposite of this one here. Well, I've said now it's minus x cubed, because I've reflected it. You can say that's y. Y or f of x, of course, be very comfortable with all that. Doesn't matter. And then finally, if I want to make it really, really stretch it vertically, make it really tall, much faster, and shift something, then let's say, how about 5 times x minus 7 cubed? Well, I know that the coefficient out front is going to be positive, so it's still going to have n behavior, sort of like that, and it's going to be shifted to the right by 7 units, just as we said before. So that point is 0, 7, and it's going to get larger much more quickly because we're multiplying everything by 5. So that's a very short example of all of the possible ones, and we can have any combination of shifts and stretches. Just be aware of which way it's going and what the function is doing as a result of these manipulations. This next section is one that gives people a lot of trouble. Students struggle with this, interpreting what it means as well as sort of manipulating it with algebra. But we're going to talk about composite functions. So let's start very simple here. And I'm going to define a function. How about the area of a circle as a function of its radius? So A is equal to f of r. A is a function of the radius. It depends on the radius because A changes when r changes. That's what the definition of a function is. Each r has a unique value. And so, what if the radius also depends on something? And I say, how about r? Let's define it as a function of time now. And it changes with respect to time. So say it starts out at 1, but as time progresses, it increases in a linear fashion. So we have r equals 1 plus t, where r is a linear function and a is a quadratic function. This is the y-intercept, and the slope is m equals 1. But now, let's say, well, I know that a depends on r, the radius, but if the radius depends on time and a depends on the radius, a must also depend on time. So we could say a new function, a of t, that's not so new, even though it seems like it. Well, if r is equal to 1 plus t, let's just shove it in. Let's just plug it in wherever we see an r. And so what that means is, simple as that. That's what a composite function is. You essentially have two functions, but they are related. So now we could say a of t is a function of time, according to this here. And something you want to get very familiar with here, a of t, this kind of general notation, well, if a equals f of r and r is g of t, well, let's also just kind of do that in general. Where I can say, okay, wherever I see an r, I shove in g of t. So that means it's f of g of t. That's how we say it. Where everywhere I see my variable, r in this case, for f, just like f of 0 is equal to, well, everywhere you see an r, plug in 0. So it's pi 0 squared. Same idea. F of minus 1, well, everywhere I see an r, plug in a minus 1, pi minus 1 squared. But now f of g of t means everywhere I see an r, I plug in the function g of t. What is that? 1 plus t. Okay, that's what that means. And it's nothing more than that. It may feel and seem complicated, but it's really as simple as that. So you do need to be very comfortable with this, especially in the context of calculus, because this comes back again and again with all kinds of derivative rules. So make sure you're okay with this basic idea. You don't have to go too crazy and do a lot of complicated problems, but you got to understand everything I'm talking about here, okay? Let's talk about something else from pre-calculus that you learned about functions, and we're going to talk about odd and even functions. So the basic definition, f is even. Remember, f is a function. anything, could be anything, f of x is what we're talking about. It's an even function if every time we see an x, we shove in negative x. So f of negative x, again, everywhere I see an x, I'm going to plug in negative x, if that is equal to the original function for all of x. So again, this is a review as always, but you should have spent a lot of time with this, understanding this. And the opposite is true if it's an odd function. So these are just definitions. So now I'm going to plug in a negative x. Remember, everywhere I see an x, I plug in negative x. And if the function is equal to minus f of x, then it is odd. For all x, of course. So graphically, what this means is that it's symmetrical if it's even, and we have a function f of x, and let's have a parabola here, because that's an even function. Everywhere, if f of x equals x squared, I plug in negative x. Everywhere I see an x, I get negative x squared. Whoa, that is x squared, which is f of x. Hooray, it is an even function. This is always true for even terms. This is also an even function. Why? Because all of the powers are even, including the constant. So this thing right here is also an even function. If all the terms are even, it's an even function. And then you also need to understand that, hey, what does it look like graphically? Well, this is symmetrical with the y-axis. Symmetry, a line of symmetry right here at x equals 0. I can reflect it about this x equals 0, and it will look the same. The function doesn't change, and it looks the same. You kind of can compare this value here and look across that line. Does it have the same value? If this is, say, negative 4, well, guess what? This is 16 and 16 for minus values. That's the definition of an even function. And the opposite is true of an odd function. So let's look at what we looked at before, x cubed. I can do a better x cubed than that. There we go. And this is x cubed. Notice I can write y up here. I can write f of x. I can write the function itself. It's all the same thing, so hopefully you're comfortable with that. But this one has symmetry about the origin. Let's do our check and say f of x equals x cubed. We're going to plug in a negative x wherever we see an x, so that becomes that, and it is minus x cubed when you simplify. Well, this is equal to minus f of x, because f of x is positive x cubed. Well, that's the definition of an odd function. So we've proved it algebraically. Now we look at the graph, and it is symmetrical about the origin, which means, hey, it's an odd function. Symmetry about the origin essentially means, hey, I'm going to reflect it about the origin, as in quadrant 1, it's going up like that, and then, well, about the origin, if this point of symmetry, not a line anymore, now it must look like that. And it does. So that means it has odd parity, symmetry, means it's an odd function. All of those things mean the same thing, if you've heard those words before. The last part of this video that I want to talk about is inverse functions. So there's a lot you could talk about here, but we're going to try to keep this very simple. Hopefully you spent a lot of time already on inverse functions, and here is just a simple reminder. So I have my normal data set. I've got some times, and so 0, 10, 20, 30 seconds. And then I have distance from my house, because I went back after another 30 seconds. So I've gone 5 meters, 12 meters, 16 meters, and then I went back 12 to the point 12 meters, right? It's just a table of data. My distance from the house in meters depends on time. Now, inverse means, well, the inputs and outputs are switched. If I switch the inputs and outputs, now the meters are the input and time is the output. So when I am 5 meters from my house, 0 seconds has passed. That's what this table says. But now we're saying it and thinking about it in a different way. Instead of it being 0 seconds, I'm 5 meters from it. Now we're thinking about it, I am 5 meters when it is 0 seconds. It's subtle, but that is how we talk about inverse functions. Now, something interesting happens here. When it's at 12, we actually have two values, and we know that breaks the rules of functions. We can still write this down, and when it's 16, we're at 20, or rather, when we're 16 meters from the house, we have passed, or 20 seconds has passed, essentially. But we are breaking the rules of functions here because each input can only have one output. And this is certainly a function. There's no rules broken here. Every input has a unique output. But this one, when we take the inverse of the function, we see that it breaks that rule. And so this function is not invertible, and that's the key you need to know. We could write f of t equals m. Same thing as saying f of x equals y, independent variable, dependent variable, just using different letters. But f to the minus 1 of t, it does not exist because we broke the rules of functions. You might remember something in the horizontal and vertical line tests. That's how we test a function graphically. Does it pass the vertical line test? Yes? Cool, it's a function. Is the function invertible? I don't know. Does it pass the horizontal line test? If it doesn't, it is not a function. That is invertible. Or rather, its inverse is actually not a function. That's pretty much what you need to know. Let me make it super clear here on a graph to remind you of that. If I have some line, I do a vertical line test. Okay, it only crosses at one point ever for a vertical line. It is a function. Certainly a function. Now what about the parabola? Well, if I say that is the parabola, it certainly passes the vertical line test in red. It's a function, but is its inverse a function? Well, let's go back to the line here. Does it pass the horizontal line test? I don't know. Does it touch the function only once for each horizontal line? Yes, it is. It has an inverse. But a parabola does not have an inverse. You have to restrict the domain, i.e. only choose the right half, or to the right of 0, to get an invertible function for x squared, restricting the domain. But in general, y equals x squared, an inverse that is a function. It is not invertible, we say. These are all the words we use. One last thing is, we talked about symmetry a little bit ago. Odd and even symmetry. I'm going to go back here. This function is even, symmetrical with the y-axis. This function is symmetrical about the origin. If it has an inverse, then it is reflected about that line. I'm going to be a little quick here, and so we can end this video, but this is something that is useful. I said something about the line y equals x. Okay, goes through the origin, y-intercept 0, slope of 1, y equals x. Beautiful. Now let's say I have some function in red. Okay, well, it's going to be something like that, I say. In fact, let me do a little bit better here and do something like that. And so reflecting this thing about that line, y equals x, because this is the original function, and now I want the inverse, it's reflected about that line, well, it means that it's going to be a reflected symmetry, something like that. Something close to that. Notice that I've just flipped it or reflected it about the line. This is the inverse of f of x. F to the negative 1 and then your parentheses x. That's how we write inverse notation. So that is pretty much everything for this video. You can find exercises and worksheets and reference sheets on the website, betterthanab.com. Make sure you are comfortable with all this, because this is all prerequisite stuff to take calculus. And you're going to struggle it's okay if you're weak in some of the areas, but you need to have a decent grasp on, let's say, 70-80% of it. Or else it's going to be really hard. The class, you're going to struggle in calculus. So do as much as you can beforehand, because it doesn't go away. It all comes back, and they expect you to know it extremely well.